Hello everyone, and welcome to the session in which we are going to implement the code for ResNet 34 in TensorFlow 2. Now, here is the ResNet 34 model right here. We have other variants like the 50, 101, and 152. After going through this section, you'll be able to implement this other variants right here. And also, you'll be able to get results like this, where we can see clearly an improvement in the accuracy of our model. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. We are going to construct our ResNet 34 model while making use of model subclassing. So you could check out the previous sections so you better understand how model subclassing is implemented in TensorFlow 2. Now that said, here we have this ResNet 34 model right here, and then the first layer we have is our convolutional layer, which has 7 by 7 filters, and they are 64 in number. Also, we note that the stride here, number of strides equal 2. So you could get all this from the paper. We have this information from the paper: 7 by 7, 64 stride 2, and then followed by a 3 by 3 max pool with a stride of 2. So we get back here, we have this 3 by 3 stride of 2. Now from this, we then get into this residual blocks. So we get back to the paper. You see, we have 3 of these residual blocks. Now it's actually this, because this is a 34 layer we're implementing right here, meaning that if you are implementing a 50 layer ResNet, then you would have 1 by 1, 3 by 3, and 1 by 1. But for the 34 version, we have 3 by 3 and 3 by 3. Now this are repeated thrice, so that's why you will notice here we have this repeated 3 times, and each one of them is our residual block. Now our residual block here, our residual block is this block right here. So we are going to later on implement this residual block here. Let's get back to the code. We have simply our residual block. You see the parameters here, number of filters 64, 64, and here 64, just exactly as we have it in the paper. You see, for each block we have number of filters to be 64. Now if we want to get into this residual block, we could or we would see exactly how it's implemented, and we would see that we're gonna have these 2 conv layers, one 3 by 3 and another 3 by 3. But for now, let's do it this way. Let's just consider that has been implemented. Now another reason why we want to implement this way is because now if we want to convert this to a ResNet 50, all we need to do now is just to update the code for the residual block, since what makes this different here is just this residual blocks right here. So that said, let's get back again. Here we have now this 4 ResNet blocks. So we have this 4 residual blocks actually. Here you see you have this is 4, and it's similar. Like here you have the 3 by 3, 3 by 3, and then here the number of channels equal 128. So you would notice here that we have 128 and we have 4 of them. Now because here we're leaving from, or we're modifying the number of channels, we need to take into consideration this number of strides we have right here, as this permits us to downsample our features. Now getting back to the code, you have this here, we have this downsampling, and then we move on 128, 128, 128. Again, here we have downsampling. Now we go to 256, exactly as is in the paper. Or we could look at this directly from here. Here we have 256, and we have a certain number of them which are aligned. We could see that in the summary here, 6 of them. Check this out here. You see we have 6 of this aligned, and then again we have 512, 3 of them as is in the paper. You see here 512, and that's it. Now from here we have the global average pooling, 2D global average pooling, and then we have this final fully connected layer with an activation which is softmax, as we've seen previously. Now that said, we just in this our call method, we're just simply gonna call all those different layers which we just created by passing in the input. So here we have our input X, which goes through each and every layer and we get the output right here. Now that said, we're going to move on to looking at this residual block right here. So we're going to implement this residual block. And now this is basically our residual block. Let's increase this so we could see that clearly. This is basically our residual block right here. So we could take one of this. Let's take this one, for example. We have this residual block right here, and then we get back to the code, see it here. Now this is our residual block. It's a layer, unlike the full model. Here we have this residual layer, and then you would see that we have this dotted boolean right here, which is true when the number of strides is different from 1. So let's run this here. Let's have this. We have dotted, and then let's specify number of strides, say equal 1. Let's print out dotted after this. So there we go. We have your dotted. We run this. Let's take this off. See, it's false. Now when we set this to 2, it turns to true. So basically that's what dotted here does. And if you get back, you will notice that let's get back to this. We had this, we selected this part, but since this isn't a dotted link, see, this link is a full line, so here our dotted variable will be false, and when we get to this, our dotted variable will be true. Now let's get back to the code. You see, we have, let's take this off. You see here we have this, which we understand already, and now we get back here. Then after, we have our 2 convolutional layers. Now we will define this custom conv2d, which again we are going to break up subsequently. So let's just understand that we have this custom conv2d, which is represented by this here. So when we have this is it right here, and this is the other one right here. Now you'll notice that the number of channels has been passed here, and the number of strides is also been passed, and that's exactly what was done here. So you see, we passed in the number of channels and number of strides. Now since by default our number of strides is equal 1, it means when we don't pass, we simply say number of strides equal 1. But in cases where we have these transitions, we have number of strides equal 2, and so our value here is going to be changed. Now that said, you see we define this conv layer, which has number of channels, kernel size 3 as in the paper, number of strides, and then we have the pattern same. So we ensure that the height and width of our input features remain unchanged. Now that said, also notice that we have this number of strides here for the second, which is equal 1. And getting back to the paper, that's simply because even when we have these transitions here, where we're getting from 64 to 128, and that we're also doing a max pooling, we have this stride, or rather that we having the striding, not max pooling, we have this stride value change for only one of the conv layers and not the 2. So you see here only 1 and not the 2, and so that's why right here you see it's only this one which actually changes. For this other one, it remains fixed, always 1. Now that said, we have the activation layer, and then if it's dotted, then we're gonna have this link right here. So if it's dotted, we're gonna have let's draw this here. We're gonna have 1 by 1 conv layer, 1 by 1. Oh, it's actually here. So we're gonna have our 1. Let's take this one off. We're gonna have our 1 by 1 conv layer just right here to ensure that this 2 number of channels match. That's the number of channels we get as input here and as output actually match up. So that's the role of this. We've seen this already. Now we get back to the code. We see here, let's take this off. We see here this here, and then we see the number of the kernel size here is 1, unlike here where we have a kernel size of 3. And then we also specify the number of channels to ensure that it matches up with what we expect. Now the number of strides here is gotten from this. So if it's 2, you're gonna have 2. If it's 1, you're gonna have 1. From here we have this set, and then we can go ahead and do the calling. So again, please check out on the previous sections where we treat model subclassing so you understand exactly what's going on. So here we have the input. You see the input, it gets into the first conv layer, then gets to the second conv layer. That's the output from the first, gets as input to the second, and then we get this output. And now let's suppose that we have a normal layer. Let's say we having this one. Let's get back to this. Let's suppose that we are working with this one right here. In that case, then the input will be added to the output directly. So here you see we have this add layer right here, this add layer from TensorFlow. It takes the output, which is this, and adds this to the input, and we now get x add, goes through the activation, the ReLU, and that's our output. Now in the case where we have this, one by one convolutional layer, specify this. In the case where we are at this position, then you'll see that we will take the input and modify it before passing it to the output, or before adding it with the output. So you see here we have this output. There we go. It remains here, and then we modify this, input. Sorry. So we take this input. There's it here. Let's take all this off and try to redraw it. So we have this. We have our res block, and then we have our output. We have the addition, which is going to be right here, addition, and then we are going to have our one by one conv layer right here, which comes and adds out with this. Now this one by one convolution is exactly what's going on right here, and that's what we defined here. So kernel size 1. Now that said, you see we add this up, and then we get our output x add. So if we are having dotted, we have that, else we go through the normal path. And that's basically why you see here we specify this sometimes and we don't in other times. Now we have understood how this works. Let's go ahead to look at the custom conv2d layer. Now the custom conv2d layer is basically made of a usual conv2d layer and with a batch norm. Remember the ResNet model, the ResNet paper makes use of the batch normalization layer. So basically here, instead of writing batch norm every time in our code, what we just want to do is combine this two, and then we have our batch normalization with our conv2d layer together. So that's it. We now run the cell. There we go. We run the cell. We again run the cell, and then we can define our ResNet 34, which is our ResNet model, which we've just seen. ResNet 34. There we go. We have the ResNet 34 summary. Let's run this. We get this error. We need to build our model. So what we're gonna do here is quite simple. We will now take this ResNet 34, and then we'll call this ResNet 34. So we'll pass in some inputs into this our ResNet 34 model. So here we'll suppose TF zeros, and then we have 1 by 256 by 256 by 3. So we have this kind of input. We run that, and we see that now we have our model. So our model summary. So this is our model summary, 21 million parameters, and that's it. Now we go to the training, but this time around we're going to include some checkpointing. So we got this from our previous session where we treated checkpointing, the model checkpointing. So here we're going to ensure that as we train, we save our best model weights. So that said, here we have this checkpoint callback. Again, you could check back on our previous sessions where we treat this callbacks. So here we have this callback, which will permit us to store the weights for our best or our best performing model, our best performing weights actually. So here we have monitor. We're going to monitor the validation accuracy. So let's take this off. Monitor validation accuracy. Save best only true. So that's it. Let's run this loss function. But before we move on, let's get back to the section where we had this parameter training right here. Now we have this custom conv2d model. Let's delete the cells. We have this custom conv2d model, which we've seen already, and then we have this batch norm layer. But it should be noted that with the batch norm layer, we have to specify whether we are in training mode or in inference or testing mode. Now the reason why we are doing this is because the parameters of our batch norm layer will react differently or behave differently in these two different modes. This means that during training, this layer will normalize the inputs with the mean and variance of the current batch of inputs. Now we've seen this already, and then when we're not training, that's when training equals false. We're in inference mode. The layer will normalize its input using the mean and variance of its moving statistics learned during training. So this simply means that we have this layer right here with some parameters. Let's call the parameters, say p. Let's call the parameters p. So you have some parameters right here, and then during training, our layer updates these parameters. But then during inference, we do not want to update these parameters as they were learned during training, and so we have to specify, or we have to pass in the training or set the training to false when we are not training the model or when we are evaluating or testing the model. Now what this simply means is that here we'll have this to training. So here you see we've passed in training, and then here we have training. So by default we could set this training to true. So by default we're in training mode, and that's what we have. Now let's run the cell and then get into our residual block. For our residual block here, we have training again. So we have training, and then since we're calling this, we'll have training. There we go. We have training, and that's it. We have training. Let's run this. We get back to our complete network, and here we're gonna have this training. So we paste that out here, and that should be fine. So now when we are not in training mode, we could specify this training parameters such that the batch norm layer or the batch norm layers parameters aren't modified. So we have that, and that's it. Okay, so we have that set. Now let's run this, and this time around we're going to set this training. So let's set training to be true. We have that true. Let's make sure that this was passed in here. So let's have this training, and the default is true. Okay, we run that, we run this, and that looks fine. Now we could set this to be false, or when we don't put any value, it means it's true. So we could set this to be false, training to be false, and that's it. So there we go, we have this set. Now let's get back to our loss function. So we were at this point, we have our metrics, we run the metrics, we compile the model, but this time around we use a higher learning rate. So one thing you could also do is, as described in the paper, decrease this learning rate as soon as the model starts plateauing. So we could start with a learning rate. In the paper it should be 0.1, although here we're going to start with 0.01. so here say you have this learning rate, and then when it starts plateauing you drop to 0.01, and then you go with that, and then it starts plateauing, you drop, and so on and so forth. So this is what they proposed in the paper, and you could always implement this, and we've seen this in some previous section where we implemented this kind of callback which permitted us to schedule our learning rate. So that's it. Let's take this off, get back to the code, and we have we've run this already, so we could start with the training. Now here we're going to train for 60 epochs, and we're going to include the callbacks. So let's have this callbacks, and we have our model checkpoint callback which we have defined here. Let's copy this. There we go. Copy this, and we have it here. So that's it. We can now run the cell. Now we've launched this training, and we've had this error here. Saving the model to the HDF5 format requires the model to be a functional model or a sequential model. It does not work for subclass models, like in our case, because such models are defined via the body of a Python method, which isn't safely serializable. Hence, consider saving to the TensorFlow saved format by setting save format to TF or using save weights. So now we're going to save these models in the TensorFlow format. All we need to do here is specify this folder, and that should be fine. The mode is max now, since we want to store the weights which have the highest validation accuracy. That's fine. Let's now run this again. Training now complete, and we achieve an accuracy, or the best accuracy, of 83.6%. We have our accuracy plot right here, and then we could evaluate the model. Here we get 82.3% and 94.6% for the top K accuracy. Now, what if we load our best model? Because the model we have here is the latest model, the very last one. Now let's load our best model and reevaluate this. Let's add this code cell. Then we go ahead and load our best weights. Here we have ResNet 34. The load weights. Then here we have our best weights. So this should be a string, since it's our folder. There's a folder where we store the weights. ResNet. We run this. That's fine, and then we evaluate our model. See here we get in this accuracy of 83.6 and then top K accuracy of 95.6%. Now we go on to test this. That's fine, and here are some results we get. Happy, angry, sad, happy. Here we miss one. We miss this one. That's 2, 3, and that's it. So we missed 3, meaning we have let's add the cell. We have 13 out of 16 answers correct. 81.2% correct. Okay, so that's it. We've gone from 79% to 83% by modifying or changing our model. Now let's plot out this confusion matrix and see what we get. There we go. Here are results, which are much better than what we have had so far.